It's a pleasure to be here. So this is some new work with Mohammed, who's in the audience, Scott, who's probably having dinner somewhere, and Paul, who I guess is busy being a Nobel Prize winner these days. So this talk is probably going to be a little bit more CS than is usual for an econ talk, and so it's probably the rate of the optimal rate of interruption is higher than usual because there will be things that are novel to some people in the audience. It's useful to have things be common knowledge. If there's something that I'm saying that seems like weird or unusual to you, feel free to interrupt and clarify. It would be a public service. So this is a paper really about what happens when you take a heuristic mechanism, a mechanism based on a near optimal allocation rule, and you consider what happens when bidders participating in the mechanism have the chance to make investments. And so this starts from, I guess one of the basic questions of mechanism design, right? Think of some setting with resource allocation with transfers, right? We're choosing who's going to win an auction. We're going to choose like who wins a landing slot at an airport. We're going to choose like, who gets to generate electricity to power the grid. Now there's a canonical answer for how we should do this, right? The question for who should get what and how much should they pay is, well, you could use a Vickrey-Clark-Groves mechanism. And this has a bunch of properties that we like. First, it's strategy proof. So it's a dominant strategy to reveal your true values to the mechanism. It has efficient allocations, right? So what it does is it takes all of the value reports and it figures out whichever allocation maximizes social welfare and it selects that. That's pretty much by definition. And the third property, which is important but less well known, is that VCG mechanisms have efficient investment incentives in the following sense. So let's start from some profile of values. And what we want to do is just change just one of the bidder's values, holding constant everybody else's value. Now, under VCG, it turns out that the change in that bidder's payoff is equal to the change in social welfare. And so that means that if the bidder had an investment opportunity, if he could pay a cost to change his value, he would do that if and only if net social welfare would increase from that investment. Now, that's a pretty neat property to have. Now, I want to start off by saying there are a few caveats to that analysis I just gave you. Caveat number one is that it assumes full information, right? To invest efficiently, the bidder has to know the prices he's going to face, right? If you were in a second price auction and you were unsure whether or not you were going to win, and you thought, well, in expectation, this investment is worthwhile, but then you didn't win the object and the investment is only worth anything if you win, well, ex post, the investment could be a bad idea. So this analysis I've given you assumes that a bidder knows the prices he's going to face. The second caveat is that if there are multiple bidders making simultaneous investment decisions, certain coordination issues can arise. You can come up with examples where my investment and your investment are strategic complements, right? So there can be good equilibria and bad equilibria. Now, the third caveat is the thing I really want to focus on in this talk. VCG mechanisms rely on exact optimization. And I mean they rely on exact optimization by the auctioneer. They assume that once you have all of the reports of everybody's values, you can, compute what the welfare maximizing allocation is and then implement that. And that, it turns out, is not always a great assumption. So sometimes in real world allocation problems, exact optimization can be infeasible. Many real world allocation problems are NP hard. So some examples, knapsack problems, which I'll get into in a moment. You can think about spectrum auctions with local interference constraints. So yay over there on the right is the interference graph for the 2017 FCC incentive auction. The nodes in that graph are TV stations. The edges in that graph represent TV stations that would interfere with each other if assigned the same channel. And so part of the question in the FCC incentive auction, asking if you could feasibly let a certain set of bidders, a certain set of broadcasters remain on the air, the TV stations, given say 8 channels, comes down to the question of whether you can color that graph with 8 colors on the nodes so that no 2 adjacent nodes share a color. That's, of course, one of the canonical NP-complete problems in computer science. So you can't exactly optimize the set of TV stations you want to have remain on the air. In combinatorial auctions, now embarrassingly, I didn't know this until a few months ago, but it turns out that even if the auctioneer knows every bidder's utility function, it can still be NP hard to find a welfare maximizing allocation of bundles to bidders. And finally, in the electricity auctions, right? So you might be aware all the time, you know, in many countries, we sell electricity by auction, right? We're deciding dynamically which power sources are on and off and who's getting compensated how much for providing power. Now, if you wanted to optimize exactly who to provide power, it turns out that the optimal power flow problem is also NP hard. So, of course, this doesn't mean that we stop running spectrum auctions or that we stop selling electricity. In practice, what happens is that we use various kinds of heuristic allocation rules. We use allocation rules that are not exactly optimal, but seem like pretty good ideas. And so our central research question is, if we take some heuristic allocation rule and we use it in a strategy proof mechanism, what's going to happen to these incentives to invest efficiently? Like, we knew that if it was exactly optimal, if it was VCG, then in a sense, investment incentives are well aligned with social welfare. What happens if we don't have exact optimization? So here's an informal overview of these results. I'll get more precise later. A natural question we might ask is, look, if I have an inefficient allocation rule in a strategy proof mechanism, is that going to lead to inefficient investments? And it turns out the answer is yes. Inefficient allocation rules have a certain kind of novel algorithmic externality. And these algorithmic externalities means the prices don't align private investment incentives with social welfare, and this leads to various kinds of inefficient investments. So, you know, the efficiency of VCG investments depends very sensitively on our ability to exactly optimize. Now, a natural next question is, okay, so maybe we can't get completely efficient investment incentives, but maybe we can get good enough investment incentives. If we have a nearly efficient allocation algorithm in a strategy proof mechanism, is that going to lead to nearly efficient investments? And it turns out, unfortunately, the answer is no. In fact, quite strongly no. Arbitrarily good allocation rules, so allocation rules that are arbitrarily close to optimal, can have arbitrarily bad investment incentives. Now, it turns out, however, that there is a simple sufficient condition that makes things okay. So if the allocation rule excludes bossy negative externalities, a condition we call XBONE, then the investment incentives are, in a sense I can make precise, going to work out okay. They won't be perfect, but they'll be pretty good. And then I'm going to offer you a characterization result, a weakening of this condition. Weak XBONE is necessary and sufficient for that second point to hold. So I want to sort of give you a concrete example so that I'm not talking completely abstractly. The running example I'm going to use in this talk is the knapsack problem. So an instance of the knapsack problem specifies a set of bidders, which I'll denote N, and each bidder has a value and a size, right? V1, S1, that's bidder one's value, bidder one's size, V2, S2, and so on and so on. And a knapsack with some capacity C. And our problem, our mission, should we choose to accept it, is to choose an allocation that's a subset of the bidders, right? To maximize welfare, the sum of the values of the packed bidders, subject to the capacity constraint. So subject to the sum of their sizes not exceeding the knapsack's capacity. Now, it's crucial, right, that this is an integer problem, right? You can either pack a bidder or not. You can't pack half of a bidder, right? It's like, think of this a bit like you're letting airplanes land on a runway. If you try to land half an airplane, bad things happen. So knapsack optimization, of course, is NP hard. There is no known algorithm that computes efficient allocations and runs in polynomial time on every knapsack instance. So it's not feasible generally to exactly optimize on these problems. Now, of course, that doesn't stop us from, in fact, trying to solve knapsack problems in practice, right? I'm going to offer you a fast algorithm for the knapsack problem. So let's start with this instance, right? We've got two little bidders, who have a value of 10 and a size of 10. And we've got a big bidder in the middle. And he has a value of 6 and a size of 12. The knapsack has a capacity of 20. Now, here's a sensible thing we might do. We might run Danzig's greedy algorithm. So the greedy algorithm is, it works like this. The first thing we do is we sort the bidders by their value divided by their size in descending order. So the little bidders have a value over size of 1, so they come to the front of the line. And the big bidder has a value over size of 1/2, so he goes to the back of the line. The next thing we do is we pack bidders from left to right. So we go to the first bidder and we put him in the knapsack, then we go to the next bidder and we put her in the knapsack. And eventually, the next bidder isn't going to fit. So we're going to stop when the next bidder doesn't fit. And so what happens is we've packed the 2 little bidders, we filled up the knapsack, and we've got a total welfare of 20. Now, a very natural question is, hold on, right? Like, what if the values are private information, right? How could we run the greedy algorithm when values are private information? So suppose that the sizes are an observable feature of the bidders, but their values are known only to themselves. That's not necessarily a problem. Here's a strategy proof mechanism that deals with it. Step 1, we ask every bidder to report their values. Step 2, we run the greedy algorithm on the reported values. Step 3, we charge each packed bidder his threshold price. So for each packed bidder, we compute the least value he could have reported while still being packed by the algorithm. That's his price. And we charge that to all the bidders who are packed. So this is a lot like a second price auction, right? We're charging you the least value you could report while still getting the object. Now, of course, the 2 little bidders, right, in order to get packed, they just need to come ahead of the big guys. So they need a value over size of at least 1/2. So they need a value of at least 5. Their threshold price is 5. The big bidder, in order to get packed, needs to come in front of both little bidders. So the big bidder needs a value over size of at least 1. That means he needs a value of at least 12. His threshold price is 12. He's below the threshold, so he's not packed. Now, I want to show you that in this little example, privately profitable investments can reduce social welfare. So this is not going to work like VCG. This is going to be a case where investment incentives are poorly aligned. What's going on? So the big bidder has not been packed and he's not paying anything. His utility is 0. Let's imagine he could pay a cost of 1 to raise his value to 14. Now, what would happen? Well, if he raised his value to 14, he would come to the front of the line, right? So the algorithm would look at him, pack him, and then say, okay, the next guy doesn't fit, I'm done. So we pack a total value of 14 instead of a total value of 20. Notice that this is profitable, right? Because his threshold price is 12, his value is 14, he pays his threshold price of 12, he's paid 1 more in order to invest. That's still a positive amount. So it's privately profitable to do this, but the investment has reduced welfare, right? We started from a welfare of 20, and now we're at a welfare of 13, right? 14 minus the cost of the investment. So what this shows you, right, is that it's not just strategy proofness that gets investment incentives to work out. There's something special about VCG that aligns investment incentives. So now I want to sort of take this knapsack stuff and remove some structure, make it a little bit more general. So these are the real model primitives in the paper. So the basic building block of the model is this thing, an allocation instance, which specifies for some set of bidders a value profile. So for each bidder, think of this as a value for being packed, a value for getting the object, a value for being in the knapsack. And it specifies this set A. These are the feasible allocations. They are a subset of the power set of bidders. Now, I'm not gonna, there's some structure on this subset, and it doesn't matter for our proofs exactly what the structure is. It could be, you know, in a knapsack problem, all the sets of bidders whose sizes sum to less than 10. It could be in a, you know, in a spectrum auction, it could be all the sets of TV stations that can broadcast on 8 channels without interference. So there's some set of feasible allocations, A, and there's a value profile, a value for each bidder. Now, of course, you can generalize that a bit, and we do that in the paper, but for now, think of it as you have a value for being packed. Now, an allocation problem omega is just a collection of allocation instances, right? We don't know in advance which instance we might encounter. Omega is the universe of problems we might encounter. Like the knapsack problem is an allocation problem. And our assumption is going to be that for all sets of feasible allocations, the bidder's possible values are a product of closed intervals. Now, why am I doing that? Well, because the paper is a lot neater if I can use the envelope theorem, and this is going to let me use the envelope theorem. An allocation rule, which I'm going to abuse language and call an algorithm, just chooses a feasible allocation for each instance. So it takes as an input, it takes as an argument, an instance of the allocation problem, and it chooses one of those allocations. So greedy is an example of an allocation rule for the knapsack problem. I'm going to use this xn. I'm going to abuse notation and just let that be an indicator equal to 1 if bidder n is packed, and 0 otherwise. A payment rule, of course, just specifies a payment for each bidder. So for each instance, a payment rule says who pays how much. And a mechanism just is a pair consisting of an algorithm, an allocation algorithm, and a payment rule. So far that's quite conventional. Now, if I start with an algorithm, not necessarily an optimal algorithm, how do I turn it into a strategy proof mechanism? Now, just to avoid ambiguity, that's the usual definition of strategy proof, right? It says for every instance and for every bidder n, reporting his true value Vn is a best response. It maximizes his utility under the mechanism. And I'm going to say that an algorithm is monotone if for any bidder n, there exists a packing threshold Tn that doesn't depend on his own value, such that if his value is above the threshold, then he's packed. And if his value is below the threshold, then he's not packed. So you may notice, of course, if I have a monotone algorithm, then it's kind of easy to make a strategy proof mechanism, right? What I do is, it's just like in a second price auction. If you're not packed, you pay nothing. If you are packed, then you pay a price equal to your packing threshold. You pay your threshold price. And that's strategy proof for the same reasons that second price auctions is strategy proof. Now, it turns out that the monotone allocation rules are the whole universe of rules we need to care about. So this is a result from Lemon et al. 2006. It turns out that there exists a payment rule P such that the algorithm paired with that payment rule is a strategy proof mechanism, if and only if the algorithm is monotone. So the monotone algorithms are exactly the algorithms for which we can have strategy proof mechanisms. So henceforth, I'm going to restrict attention to these monotone algorithms for the rest of the talk. Basically, when I say algorithm, think monotone algorithm. Now, but by the way, just to simplify the problem further, you might say, well, maybe it matters for investment incentives which payment rule we pick. It turns out that doesn't matter. It turns out that for any algorithm, the corresponding strategy proof payment rule is essentially unique. So if a mechanism is strategy proof, then there exist these functions Fn, which don't depend on bidder n's value, such that the payment bidder n makes is equal to the indicator for whether or not he's packed times his packing threshold. So that's just his threshold price, plus these functions Fn. Right? So you can see these Fn functions are strategically irrelevant, right? He can't change those by changing his report. So, and he can't change those by changing his investment. So a corollary of this proposition is that any two strategy proof mechanisms for the same allocation algorithm yield the same investment choices. So the investment incentives in a strategy proof mechanism are going to be entirely pinned down by properties of the allocation algorithm. Cool? Now I want to have a bunch of desiderata we might want to have an algorithm satisfy. We want it, so this, I'm going to use this function W of X to denote the welfare achieved by some algorithm X at some instance VA. That's just the sum of the values of the packed bidders at that instance. Now, you know, one thing we might want is we might want to have efficient allocations. What does that mean? It means that for every instance, the welfare achieved by the algorithm is equal to the maximum welfare you could get where you're maximizing over the feasible allocations. Another property we might want is to have efficient investments. Now, in words, you know, this gets a bit messy in math, but in words, what this says is, look, suppose that bidder N, knowing his threshold price, so knowing the other bidder's values, can invest to change his own value. We'd like him to make that investment even only if the welfare gain is going to exceed the cost of doing so. And so that's this in math. It says for any instance, for any change in that bidder's value, V tilde N, and any cost of that investment, C, what is this saying? The bidder's utility from making the investment rises if and only if the welfare net of the investment costs rises, right? So that's exactly the thing I showed you on the first slide, right? This is saying, starting from any instance and for any change that bidder might make to his value, he wants to make that change if and only if society wants him to make that change. And so you can think of this a bit like long-run adjustment to prevailing prices, right? Like what's going on is, you know, you're participating in lots of electricity auctions. You kind of know, you know, on a sunny afternoon, on a Monday, this is roughly what the electricity price is. You're choosing whether or not to ramp up your own power plant, right? You're doing something that affects your marginal cost of provision in the afternoon, right? We'd like you to make that choice if and only if it's socially beneficial, given the algorithm we're doing. Cool? Okay, so that's a whole bunch of stuff. It's probably a good moment to take a pause in case there are questions, points of clarification.
Hi, Shengwu.
Yes?
So I have a question regarding, so you have mentioned you're going to focus on implementable, you know, strategy-proof mechanisms. So in this setting, do you have any strategy-proof mechanism other than the generalization of the VCG?
No. So it turns out that, well, it depends what you mean. So there are strategy, so every monotone allocation rule has an associated payment rule, right? So there are as many strategy-proof mechanisms as there are monotone algorithms, and there aren't any more of them, right? So this proposition I showed you on this slide says that basically once you're looking at these threshold prices, I mean, up to this sort of additive term at the end, those are all of the mechanisms we need to worry about.
Yeah, no, what I don't mean, so this is kind of like, you know, the revenue equivalent sort of, you know, it's a type of revenue equivalence result. I mean, the actual allocation rules. So what I mean by generalized VCGs, I mean, you know, something that looks like an affine maximizer.
Yes.
Right.
So for instance, the greedy algorithm I showed you earlier, right? That's not an affine maximizer, right? It's a sort of more primitive myopic algorithm than that, right? It's greedily packing the best until we hit the end, and then that's it, right?
I see. Okay. And that is allowed, so by the monotone algorithms.
Yes.
Okay.
Yes. Greedy algorithms are monotone algorithms.
Okay. Thanks.
Great. That was hugely useful. I should have emphasized that more. All right. So in some sense, this proposition, this is not original to us. I've given you a bunch of desiderata. We want efficient allocations. We want the mechanism to be strategy proof. We want it to have efficient investments. And this Rogerson 92 observes that the VCG mechanism satisfies all three of these. And the intuition you should have is exactly that the VCG mechanism internalizes all the externalities, right? Each bidder's threshold price is exactly equal to the welfare loss to other bidders when he's packed. And because of that, when you're making an investment choice, you're already taking into account the effect of your investments on the other bidders. Now, this, it turns out, is a very special property of VCG. Other heuristic mechanisms can have these algorithmic externalities. So if you start from a heuristic allocation algorithm, it turns out that the threshold prices may not reflect the full social cost. They may not reflect the welfare losses to other bidders from packing you. So remember this greedy example, right? The big bidder's threshold price is 12, but when he invests to raise his value, he causes a fall in the other bidder's welfare of 20, even though his threshold price is 12. So there's an algorithmic externality because the big bidder, by investing, is affecting how good an approximation the greedy algorithm gives us, right? He's causing effects on other bidders which are not reflected in his prices. And so it seems like a natural question to us, for which allocation algorithms do threshold prices actually do the work of internalizing all the externalities? Which of the allocation algorithms yield efficient investments in the same way VCG does? So let me show you a weakening of that property I gave you just now. Here's a weakening of efficient allocations. So here, the differences are in red. Range efficient allocation says that for every A set of feasible allocations, there exists a restricted set R such that for every value profile V, the welfare achieved by the algorithm is equal to the welfare you would achieve by maximizing over the set R. Now, this is a subtle property. It helps to note the order of quantifiers. Notice that R depends on A, but it does not depend on V, right? So you could potentially have a different set R as the feasibility constraints change, but you can't have a different set R as the value profile changes. In particular, what this means is that if for some generic value profile, some value profile where no two allocations are tied, the algorithm outputs some allocation A star, we can infer that A star is in this restricted set R. And what that means is that for all other value profiles V prime, the algorithm must do no worse than it would by selecting A star. Now that's restrictive. For instance, for the knapsack problem, the greedy algorithm does not satisfy range efficient allocations. Like there are certain allocations which it selects, but then when I change the value profile, it does worse than it would have by staying still and keeping that old allocation. Now it turns out that only these range efficient allocation algorithms manage to avoid algorithmic externalities. So this is actually new. Here are three desiderata: range efficient allocations, strategy proofness, and efficient investments. And it turns out that for any mechanism with a monotone algorithm, any two of these implies the last one. So if you have range efficient allocations and your mechanism is strategy proof, it has efficient investments. If you have range efficient allocations and you have efficient investments, then your mechanism is strategy proof. It turns out that for these algorithms, either efficient investments or strategy proofness equally pin down kind of the VCG prices. Now, this last one is actually the difficult observation. It turns out that if you have efficient investments and strategy proofness, so never mind directly, we're not assuming any need for efficient allocations. These two desiderata imply range efficient allocations. So what that means is if you want to avoid these algorithmic externalities, if you want to align investment incentives in a strategy proof mechanism, essentially the only allocation algorithms you can choose from are the ones that are range efficient. And so roughly what that says is that if you have a strategy proof mechanism, the only way you can get efficient investment incentives is you've got to constrain the allocations you consider. You've got to throw out, ahead of looking at the values, certain allocations and say, I'm going to look at a restricted set. You've got to keep doing that until exact optimization becomes feasible. Now that's a pretty restrictive result, right? In computationally hard problems, if you do this, you're going to sacrifice potentially a lot of allocative efficiency, right? But what this theorem is saying is that the connection between efficient investments and exact optimization is pretty intimate. Like, it really does rely on our ability to exactly compute the optimum potentially on a restricted set. So for instance, right, one thing you could do is you could say, look, there are too many bidders for me to consider. I'm only going to consider putting the first 3 bidders in the knapsack. The other bidders I'm going to ignore, right? That's range efficient allocations, right? I'm only going to consider packings that involve the first 3 bidders. Now, of course, when exact optimization is infeasible, we don't throw up our hands and say, we're not going to run a mechanism. What happens is we approximate. And there is a vast computer science literature that studies fast algorithms for hard problems. Now, these algorithms typically violate this REA property, but they are approximately optimal in a precise sense. And this is this precise sense. So we talk about an approximation ratio beta. So for some beta in between 0 and 1, we say that an algorithm acts as a beta approximation if for every instance of the allocation problem, we have that the welfare delivered by the algorithm is at least beta times the welfare under the efficient allocation. So to give an example, the greedy algorithm is typically a 0 approximation on the knapsack. That's to say, in the worst case, greedy can get an arbitrarily small fraction of the optimal welfare. But, you know, like there's a standard way to fix that. So you might imagine saying, let's take this algorithm called smart greedy. What smart greedy does is it runs the greedy algorithm, it looks at that output, and it compares that output to the single bidder with the highest value, and it packs whichever is better, either the greedy output or the single bidder with the highest value. It turns out that that already gives you a meaningful approximation. The smart greedy algorithm is a half approximation for the knapsack problem. So for every instance of the knapsack problem, smart greedy gives us at least half of the first best. Now, I want to say, like, this is an unusual way of looking at approximation, right? This is implicitly a worst case standard. It's saying you've always got to be within a fraction beta of the exact optimum. And not only that, it's fractional, not additive, right? So both of these things are a little bit unusual to economists, and I want to say a little bit about why computer scientists do things this way. So we might ask, why do computer scientists do this worst case analysis? Well, it turns out that the theory of computation is built around worst cases, right? So complexity classes like P and NP are defined with respect to worst case runtimes. So if you want your proofs to play nicely with what we know about computation, worst case is a natural way to do it. Now, why do they use these fractional approximations rather than additive approximations? Well, it's because in genuinely computationally hard problems, there are no fast algorithms that give us additive approximations. Fractional approximations are all that we have on the table. But not just that, they've got this useful property, right? That this way of looking at algorithms sort of concatenates, right? So if you take an algorithm that's within half of the optimum and an algorithm that's within 90% of the optimum, and one algorithm calls the other as a subroutine, then you can just multiply their approximation ratios, right? So that's a neat property to have that it turns out is useful. So I'm not completely wedded to this way of looking at the world, but this is the sense in which computer science approximation algorithms can be said to be approximately optimal. And we want to be able to talk their language. We want our results to speak to their results. So we're going to adopt their notion of approximate optimality going forward in this paper. Cool? Questions, thoughts? Okay, so pulling back a little bit, right? We're asking ultimately the question, which algorithms lead to good investment incentives? Suppose we start with some monotone algorithm and we run the corresponding strategy proof mechanisms. Now, we know that range efficient allocations and strategy proofness together imply efficient investments. Moreover, we know that in general, approximately efficient allocations plus strategy proofness are going to imply inefficient investments. Somewhere there's going to be an investment that the bidder would want to make that a social planner would not want him to make. Now, a natural question is it true that approximately efficient allocations are going to lead to nearly efficient investments? Like, we might hope that if your algorithm is within 99% of the optimum, then maybe the investment incentives look kind of okay. Well, okay, to ask that question, well, we're gonna have to measure welfare, including investment. So suppose some bidder N chooses between either having a value V upper bar at some cost C upper bar, or he takes his original value V lower bar for free. So this is an investment technology, which I'll denote IN. An investment technology says, here's a new value, which you can have for some cost, or you can keep your original value for free. Now, given an investment technology and his threshold price, our bidder is going to choose an investment to maximize his payoff under the strategy proof mechanism, right? So B star is just his set of best responses given the investment technology, given the other players' values V minus N, given the feasible allocations A, right? So it's like this bidder understands the algorithm, he understands the mechanism, he's gonna best respond, he's gonna choose whichever investment maximizes his own utility. And of course, welfare including investment, that's just going to be the minimum among that bidder's best responses of the allocative welfare minus the cost of the investment that he chooses. Now, you might say, does it really matter? Like, it turns out it doesn't matter whether we take the minimum. Like, remember, an investment technology, you're choosing between two things. Generically, you're not going to be indifferent. So generally, this is going to be singleton. It turns out that any selection from the best response correspondence will do for our results. I'm just choosing the minimum to avoid ambiguity. Okay, so we're going to need a benchmark to compare this to, right? We've defined welfare of an algorithm under investment. Now, what's our benchmark? Our benchmark is going to be pretty demanding. We're going to compare it to having efficient investments and efficient allocations. So this W bar star, that's the first best given the investment technology. We're maximizing over the investments, and we're choosing an allocation that maximizes welfare. And we're going to say that an algorithm acts as a beta approximation with investment if for any investment instance. So an investment instance specifies an investment technology for some bidder N, values for the other bidders, and feasible allocations. We have that the welfare delivered by the algorithm, including investment, is at least beta times the first best welfare, including investment. Now, the subtle thing about this is that this is allowing for inefficient investments, right? It's saying that there can be times where, you make an investment even though the social planner doesn't want you to make it, provided that welfare net of investment is at least beta of the first best for some beta less than 1. Cool? Okay, so it's natural to ask, right? We've got this notion of allocation algorithms, right? When we can lift, hundreds of algorithms from computer science textbooks and look at their allocation guarantees. And we can ask what happens when we expand the model a bit, when we add these investment technologies. And so you can think of this as a sort of minimal robustness test, right? It turns out that the guarantees can't get any better. So if for any beta, if X is not a beta approximation, X is not a beta approximation with investment. Why is that? Well, I can define a kind of trivial investment technology, right? I can say you can have a value 10 at cost 0 or a value 10 at cost 0, right? And obviously that's just the same as if you couldn't change your value. So you can't get any better with these investments, but the approximation ratios can get a lot worse. So here's a proposition. For all beta strictly less than 1, there exists a beta approximation for the knapsack problem that is no more than a 0 approximation with investment. So you can get arbitrarily close to optimal on the knapsack. And no matter how close you are, closeness to optimality by itself does not mean that the investment incentives are at all okay. So this implies that being a beta approximation in allocations and having a strategy-proof mechanism is not enough to deal with investment incentives. Now, of course, it's natural to say like, well, that depends on which kinds of algorithms we're talking about and like what the bad cases look like. So let me show you the bad case, right? How can it be that the guarantee gets worse when we're having investment opportunities? Okay, so I want you to think of a satisficing algorithm. The way this satisficing algorithm works is if bidder 1's value is at least 99% of the total value, sum up everybody's value. If bidder 1 is at least 99% of the total, then pack just bidder 1, call it a day. Otherwise, optimize exactly. Now, of course, this satisficing algorithm is by construction a 0.99 approximation, right? I'm always 99% of the first best. Now, suppose we have 2 bidders and both of them fit in the knapsack. This is how the algorithm outputs things, right? If bidder 1's value is at least 99% of the total value, then we pack just bidder 1. Otherwise, we're going to exactly optimize, so we'll pack both of them. Notice that bidder 1 is always getting packed. And since she's always getting packed, her threshold price is 0. Now, suppose she could either have a value of 0 at a cost of 0 or a value of k plus epsilon at some positive cost k. Now, of course, right, if she has a value of 0, her utility is 0. If she makes the investment, she gets a value k plus epsilon from being packed minus the cost k. She gets epsilon. For positive epsilon, it's profitable to invest. Notice that if I took k large enough, right, then only bidder 1 is going to get packed because bidder 1 is going to take up a large enough fraction of the total value. What's the welfare the algorithm delivers? Well, it's k plus epsilon minus k. It's equal to epsilon. What's the first best welfare? What would a benevolent social planner do? A benevolent social planner would say, make the investment. It's worth it to make the investment, and I'll pack you both. So a benevolent social planner gets welfare V2 plus epsilon. Notice this means that the approximation ratio of this algorithm, once we add investments, can't be any better than epsilon over V2 plus epsilon. And of course, I could choose epsilon arbitrarily small. What this says to you is that even though this algorithm is always within 99% of the optimum in an allocation problem, once I add an investment, it can achieve an arbitrarily small fraction of the social optimum. Now, I want to point out to you like a weird property of this algorithm, like something that should, sort of cause us unease. This algorithm has what we could call a special kind of externality, a bossy negative externality. Now, what do I mean by that? Well, when we start beta 1's value at 0, she's packed. And when we raise her value to k plus epsilon, that doesn't change whether or not she's packed. Yet it's reducing the welfare of bidder 2, right? So this is a bossy externality because, well, it's bossy because I'm changing bidder 1's value in a direction that isn't going to change whether or not she's packed. It's a monotone algorithm. It's a negative externality because it's harming the welfare of the other bidders. Now, it turns out, by the way, this is not just a problem for our toy algorithm. There's what's called a canonical fully polynomial time approximation scheme for the knapsack problem. Now, this approximation scheme basically says, look, you can get within a ratio 1 minus epsilon of the optimum using an algorithm that runs in time polynomial in the sort of length of the description of the instance and polynomial in 1 over epsilon. Now, it turns out that there's a standard way this fully polynomial time approximation scheme works that involves a certain kind of rounding that makes it vulnerable to exactly the same problem I just showed you. So the canonical fully polynomial time approximation scheme for the knapsack can get arbitrarily close to optimal, but has no meaningful ratio once you add these investment technologies. So, there are real algorithms that we might consider that have this vulnerability. So a natural question, right, we want to ask is, what's a sufficient condition that would make a guarantee robust to investment? And it turns out that what you need to do is to forbid these kinds of negative externalities, these bossy negative externalities. So, in words, this condition says this, like, let's start from some instance, value profile, feasible allocations. If we raise the value of a packed bidder or lower the value of an unpacked bidder, then the total welfare of the other bidders does not fall, right? So this is a property of algorithms. And so that's just this in math, right? It says an algorithm is XBONE. It excludes bossy negative externalities if for any allocation instance and any V prime n, any change in the bidder's value, if bidder n is packed and we raise her value, or bidder n is not packed and we lower her value, then the welfare of the other bidders under the algorithm does not fall. Okay, so this is forbidding exactly that kind of phenomenon I showed you one slide ago. And this is, I guess, the sort of main positive result. The theorem says, give me any beta, any approximation ratio. If the algorithm is XBONE and a beta approximation, then it's still a beta approximation with investment. So this is a kind of robustness property. It's saying, for a special class of allocation algorithms, right? To the extent, a smart computer scientist comes to us and hands us an allocation algorithm for our problem. And we want to know if it's going to cause us problems when we add investments. And this is kind of a simple sufficient condition that gives us a guarantee. It says, if the algorithm checks this box, then we know that its approximation ratio is not worse when we add investments. Now, it can't get any better, right? I argued that a few slides ago. But we know at least that to the extent it does well, it's going to keep doing well when I add investment opportunities. Now, here are some examples of XBONE algorithms. First, any exactly optimal algorithm is XBONE, right? Like, if I raise the value of a packed bidder and you're exactly optimizing, well, you don't change the allocation, so you're fine. If I lower the value of an unpacked bidder and you're exactly optimizing, you don't change the allocation, so you're fine. the greedy algorithm is XBONE. Why is that? Well, you know, think about, I've sorted all the greedy, you know, I've greedily sorted the bidders into a line, right? Value over size. If I raise the value of a bidder who was being packed, the algorithm will terminate at the same spot. So we do at least as well as before. And if I lower the value of an unpacked bidder, well, the algorithm is going to terminate before it even meets that bidder. So we're going to do at least as well as before. So it turns out also that there's another neat property. If you give me a set of XBONE algorithms, the algorithm that takes the maximum from that set, that takes whichever output looks best from that set, is also an XBONE algorithm. So for instance, the smart greedy algorithm, right, is XBONE and a half approximation. And this theorem then means that not only does it always get within a half in the allocation problem, it also gets within a half in the corresponding mechanism, no matter which investment opportunities we add. And why is that? Well, because we can construct smart greedy as the max of the greedy algorithm, the algorithm that packs bidder 1 for sure, the algorithm that packs bidder 2 for sure, and so on and so on. These are all XBONE algorithms, so their max is XBONE, and we're fine. Now, there's a special class that you may also have encountered elsewhere in market design. Any non-bossy monotone algorithm is XBONE. Now, what's a non-bossy algorithm? Non-bossy means that if I change a bidder's value without changing whether he is packed, then the allocation is not changed. So this is sometimes thought to be a like separately useful desideratum, right? It's saying like in an incentive auction or, you know, in some kind of high stakes auction, you don't want to let one bidder cause trouble for the other bidders by changing his report, right? In particular, cause trouble in a way that doesn't even have any stakes for him on the table. Now, certain algorithms that we really do use have this non-bossy property. So for instance, the 2017 FCC reverse auction that I told you about at the start, right? That uses a kind of greedy rejection algorithm to choose which TV stations should remain on the air. That greedy rejection algorithm is non-bossy, so it's XBONE. Okay, so what I want to show you is a proof, right? I want to, because I'm maybe inordinately proud about how simple this proof is. It actually just fits literally on one slide. So what am I going to do? I'm going to take any investment instance. So an investment instance, remember, specifies an investment technology for the bidder N, values for the other bidders, and feasible allocations. I'm going to take any instance such that the investor is not indifferent. Now I'm going to suppress all these welfare functions, right? They depend on V minus N and A, but I'm not going to be moving those about. So to reduce clutter, I'm going to suppress the dependence on these things. I'm just going to look at the argument that's moving. Now notice that if the investment doesn't even cover its costs, right? That's saying if V upper bar minus C upper bar, the value from the investment net of its cost is strictly lower than the original value, well, then a self-interested investor is never going to make that investment, right? The investor faces a threshold mechanism. This investment can't even cover its own costs, so it's not worth making it. But of course, that's also first best, right? If the investment doesn't cover its own cost, a benevolent social planner would not make that investment either. So the interesting case is when the investment at least covers its value, right? When V upper bar minus C upper bar, that's the net value of the investment, is at least the original value. Now, observe that the first best welfare under investment is equal to the allocative welfare at the net value. Now, this is a little subtle, so let me explain, right? Now, imagine you're a benevolent social planner, right? If you pack the investor, if you pack this bidder, and the investment at least covers its cost, you might as well have the bidder invest, right? So how much value do you generate from the bidder if you pack him? You generate V upper bar minus C upper bar, right? The welfare at the net value. Sorry, you generate the net value from this bidder. Now, what happens if you don't pack this bidder? Well, if you don't pack this bidder, there's no reason for you to pay the investment costs, right? So if you're a benevolent planner, what you say is, well, I'm going to take the free investment at zero cost. So how much value do you generate if you don't pack this bidder? Well, you get no value from this bidder, you get 0. So the investment problem from the first best perspective is it's just as though this bidder has a welfare at his net value, right? So that says the investment welfare, the first best welfare of the investment problem is equal to the allocative welfare of the instance where bidder N has his value net of investment costs. There are just 2 cases to consider. The first case is suppose N would be packed by the algorithm at this net value, at the value net of investment costs. Well, the investor is facing a threshold price, right? He's facing a strategy proof mechanism. If he's packed at his net value, then the net value exceeds the threshold. So it's profitable to make this investment. The investor is not indifferent, so he chooses to make that investment. What does this say? Well, beta times the welfare, the first best welfare of the investment problem, I've already argued is beta times the allocative welfare at the net value. But beta times the allocative welfare of the net value is no more than the welfare that the algorithm delivers at the net value, right? That's what it means to be a beta approximation, right? At this instance, the algorithm has got to be delivering at least beta of the first best allocative optimum. What's this saying, right? What am I doing here? I'm taking the bidder at his net value, he's packed at his net value, and I'm raising his value by C upper bar. Right? I'm raising it from V upper bar minus C upper bar all the way to V upper bar. Now, the algorithm is monotone. So when I raise the value of a packed bidder, he's still packed. The algorithm is XBONE. So when I raise the value of a packed bidder, the welfare of the other bidders does not fall. So total welfare has to rise by at least the change, C upper bar. And that's exactly what this line is saying. And of course, on the right, that's just, of course, because the bidder investor is investing, that's the welfare under the algorithm at that investment instance. And then the other case proceeds very much the same way. The other case is suppose the bidder is not packed at the net value, right? When he reports his net value, he would not be packed. Well, okay, that means that his net value from the investment is below his threshold price. So it's not worth making the investment. And the investor is not indifferent, so he chooses not to make the investment. Everything is proceeding exactly as before. The only difference is this line here, right? What am I doing here? I'm taking the welfare at the net value under the algorithm. Now, the investor is not packed at this net value. And now I'm lowering his value from the net value down to his original value, V lower bar. So I'm lowering the value of an unpacked bidder under the algorithm. But again, the algorithm is XBONE. When I lower the value of an unpacked bidder, the welfare of the other bidders can't fall. So we've got to be doing at least as well as before. And so that gives you both cases, right? In both cases, the welfare that the algorithm delivers when investment is possible is at least beta times the first best welfare when investment is possible. And so you can kind of see what's going on here, right? Like, it turns out that you don't need to forbid all of the externalities, right? You only need to forbid certain kinds of externalities, specifically the bossy negative externalities. And, you know, there can be cases where the investment incentives are not quite right, even in an XBONE algorithm. But to the extent that that is true, then that is already reflected by the original approximation ratio, by whatever the allocative guarantee is, even before we were thinking about investments. Cool. Okay, so this is probably a good point to take a pause because that was, I recognize, very heavy going. Questions, thoughts, cries of relief? Cool. Okay. All right. So I'm going to show you a sense in which this XBONE condition could get weakened a little bit. So we want to know, so let me back up a bit, right? a natural thing that like economists will say, right, that I feel when I see worst case analysis is that sometimes we can rule out certain pathological worst cases, right? We can say, look, you know, the worst case doesn't really have the structure. That worst case is sort of, you know, unreasonable to believe in. And it turns out that there is a language that lets us express ideas like this. So for any allocation problem omega, we can think of subproblems omega prime. This is just a problem whose instances are a subset of the original problem. Now, of course, an approximation ratio can only improve on subproblems because an approximation ratio is defined by the worst case. So for instance, if no bidder's size exceeds 10% of the knapsack's capacity, then greedy is a 0.9 approximation, right? It's always getting 0.9 of the optimum, right? So if you thought that in a knapsack problem, the sort of worst cases where one bidder took up a huge fraction of the knapsack were unreasonable, this is a way to say, you know, those cases are unreasonable. Really, the greedy algorithm is better than we're giving it credit for. Now, notice that XBONE is a property that is inherited on all the subproblems. So a corollary of the theorem I just gave you is that if an algorithm is XBONE on a problem omega, then for any subproblem omega prime and any beta prime, if the algorithm is a beta prime approximation on omega prime, then it's a beta prime approximation with investment on omega prime, right? So this is saying if you give me a subproblem, the algorithm's allocation guarantee can potentially strictly improve on that subproblem. And of course, because XBONE remains on that subproblem, we can say that the algorithm is good even with investment on that subproblem. So for instance, what this says is that greedy is a reasonable heuristic for the knapsack problem when the bidders are small, and it remains reasonable even when we add investment opportunities. Now let me ask then, in a sense, having set all that up, is it possible to weaken the XBONE condition I just gave you and still have these allocation guarantees be robust in this nice way, that they're inherited on all subproblems? So here's a theorem, and it's got one term that I haven't defined yet. Let X, the algorithm, be a beta approximation on omega for some non-trivial beta, for some beta strictly more than 0. These two statements are equivalent. First, that X is weakly XBONE on omega. And second, for any subproblem omega prime and any beta prime, the allocation guarantees get inherited. So if X is a beta prime approximation on omega prime, then it's still a beta prime approximation with investment on omega prime. So what is this saying, right? It says there's some condition, which I'll define on the next slide, that is necessary and sufficient for this property that on every subproblem, the allocation guarantee is robust to adding investment opportunities. So another way of looking at this theorem is it says, if the algorithm fails this weak XBONE condition, then I can locate a subproblem, a subset of the instances of the original problem, such that the algorithm's approximation ratio gets strictly worse on that subproblem when we add investment. Okay, so you might ask, why does this theorem have this structure? Well, essentially it can be that, imagine the algorithm is XBONE almost, in almost all cases. It only fails XBONE when it's already doing very, very well. But there are some cases where its allocation guarantee is terrible. So the fact that it fails XBONE when it's doing really well isn't going to harm its guarantee because its original guarantee was already terrible, right? What this theorem is saying is I'm going to be able to locate a subset where the algorithm's doing well and show you that on that subset, it's going to do worse with investment, right? If the algorithm fails this condition. So what is weak XBONE? Like what is weakly XBONE? It turns out that you can relax this, but you can only relax it for certain kinds of downward changes. So the only difference on this slide is the red bits, right? Other than that, this is the same condition as before, right? So the algorithm is weakly XBONE if for any instance and any change in bidder n's value, v prime n, if that's the same as before, if n is packed and we raise his value, or if n is not packed and n is in every efficient allocation at that instance, and we lower his value, then the welfare of the other bidders doesn't fall. Right, so this is a weaker condition because this second clause has become more demanding. Now, there's just one thing about this condition. It's just not as useful as the XBONE condition. And why is that? Well, if I knew how to compute efficient allocations, we wouldn't be in this mess, right? The whole point of this is that we want to deal with problems where we don't know a lot about what the efficient allocations look like. And what this is saying is that the places we can safely weaken XBONE are cases where we know at least this much about what the efficient allocations look like. We know that this bidder wasn't going to get packed in any efficient allocation, and we're not packing him. And those are the cases where we can squeak by and weaken XBONE just a little bit. So in some sense, what does this theorem I just showed you really say, right? This theorem is saying that XBONE is not necessary, right? It's sufficient, but not necessary. Weak XBONE is necessary and sufficient, but it's a lot harder to check. And in some sense, for practical purposes, if you want to know whether your algorithm does well, you're probably checking XBONE. Weak XBONE is saying there's a little bit of slack, right? There's a little bit of slack in the downward direction, but you need to be able to do something clever in order to check that that is okay.
So basically, for all intent and purpose, this is just like a maximal domain result.
Yeah, this is exactly a maximal domain result. In fact, I was talking to Scott, and this was also, when we first came upon this result, that was exactly Scott's reaction. So I think there's a sort of co-author mind meld going on here. Cool. All right, so I would say, like, I'm not going to cover these in huge detail, but there are some natural extensions you might make. Like, you know, I've been talking in value maximization language. There are lots of natural cases like procurement auctions where you're in a cost minimization problem. Every result extends in a natural way. You just flip all the signs. So things like traveling salesman problems, Steiner tree problems that are standard when you're like building a network and have to procure links in the network. These get, you know, like there are versions of these results for those. I've shown you these for cases where the types are one-dimensional, right? You have a value for being packed and your value for not being packed is normalized to 0. You can extend these to multi-dimensional types. There can be multiple ways to be packed. So, you know, you might imagine that television stations might care which channel they're on, right? Maybe they like the higher channels better, right? You can, you know, you can express that. You might imagine that, you know, we're choosing, you know, I can give you a red object or a blue object, and you can have distinct preferences over whether you get red, blue, or both. All of the main results extend to cases with multidimensional types. Efficient investments are still going to need exact optimization, and a generalization of XBONE is going to still be fine. It's going to be sufficient for the guarantees to pass through with investment. You know, I mentioned combinatorial auctions at the start. It turns out you can also extend these results to combinatorial auctions with certain kinds of substitutes preferences. Technically, you can get fractionally subadditive preferences, which include all the gross substitutes preferences. But you need to make a restriction on the investment cost. Basically, you need it to be that you know, investing in, it's got to be that investing in, you know, good A and investing in good B are not complements with each other. Cool. And so, you know, like you can do that, but I'm not going to belabor it. Like at a very high level, what this paper is saying is this. Look, like in a strategy proof mechanism, if you want to get investment incentives exactly right, that's going to require exact optimization. You're going to need to look at these range efficient allocation algorithms. And in hard problems, this is infeasible. You can't exactly optimize over everything. And if you restrict the range of allocations you look at, you're potentially losing a lot of allocative efficiency in order to get investments correct. Algorithms can choose near optimal allocations and yet be very far from optimal when we add investments. And I showed you some examples. The problem with this is that these algorithms have these novel algorithmic externalities. There are cases where when you change your value, you change the quality of the algorithm's approximation. And these bossy negative externalities in particular are the things that cause the real problems. If the algorithm manages to exclude not necessarily all algorithmic externalities, but at least these kinds of externalities, then things are good. Then its guarantee on any subproblem remains the same when we add investments. And if you want to weaken it a bit, weak XBONE is necessary and sufficient for the conclusion, but for practical purposes, we probably check XBONE rather than weak XBONE. And you know, in the spirit that the bliss point for presentations finishing is probably somewhere internal, that's all I had planned to say, and I'm happy to like chill out and take questions or just chat.
Well, before taking questions, just thank you for an excellent talk.
Thank you so much.